Hello everyone. Today I am going to discuss one type of chromatography, that is thin layer chromatography. Chromatography is a main field of analytical chemistry. Analytical chemistry is the study of separation, identification and quantification of the chemical component of natural and artificial materials. The separation of components is often performed prior to every analysis. So, it is an important step. It is an important step that can help in all type of analytical determinations. Separation process convert mixtures into their constituent parts. In general, separations are based on differences in physical and chemical properties like shape, density, size, mass, boiling point, and chemical affinity. There are two types of separation methods: classical methods of separation and modern methods of separation. Whenever we say classical methods of separation, these methods are old methods which have invented way back, but they are still being used in different fields of chemistry. You all are very much aware with these three terms: precipitation, distillation, and extraction. All these three terms are considered as classical methods of separation. First method is precipitation, in which precipitate and filtrate are separated on the basis of solubility product value of the compound. Second one is distillation, in which compounds are separated on the basis of boiling point. Generally, this method is used for the separation and purification of the liquid samples. Third one is extraction, or commonly known as solvent extraction. This method is generally used by organic and analytical chemists. In this method, compounds are separated on the basis of their solubility in different solvents. Although classical methods of separation are there, but growing demands in last 50 years have helped in emerging with new separation techniques, and people and scientists consider chromatography as a newer method of separation, which can help in reaching new and new horizons in the field of research and industry. Chromatography was originated with the work of Russian scientist Michael Sweat in 1906. He was working on plant pigment, and his interest was to find out whether the leaf extract, which is green in color, is having one or more components. To check the number of components present in the leaf extract, he prepared a glass column filled with calcium carbonate, and extract of plant pigment dissolved in ether or made in ether is placed at the top of the column. He further the further washing of the column with petroleum ether, he observed different colored bands. That was the beginning of the chromatography. Sweat named this process as chromatography after the Greek words chrom means color and graphy means to write. It means chromatography as writing with color. According to IUPAC, chromatography is a physical method of separation in which the components to be separated are distributed between the two phases, one of which is stationary phase, while the other moves in a definite direction, which is mobile phase. Or we can say chromatography is a technique for separating mixtures into their components in order to analyze, identify, purify, or quantify them. This slide shows the retention mechanism of the compounds in the chromatography. Particularly here, we are taking the example of thin layer chromatography. In the first side, this side, you can see at the left side, the mixture of the sample mixture is spotted. This is the sample mixture, and right side shows the TLC plate after the separation. You can see the blue color travel from the top to bottom. This is the mobile phase. This distance is traveled by the mobile phase. Other thing you can see, there are four types of compounds which are denoted by color: yellow, red, blue and black. You can see blue color compounds traveled from, you can see the yellow particles moved the most and the blue particles moved the least. Particles which moved the least, that means yellow particles. Yellow particles have a stronger attraction or affinity towards the stationary phase and lesser solubility in the mobile phase. Similarly, particles that is yellow with color have highest attraction, that are moved most, have highest attraction or highest solubility in the mobile phase. They have very little interaction with the stationary phase. You can see the affinity of different compounds with respect to stationary phase and the mobile phase in the bottom, at the bottom, given in the table. Remember, the particles move the most with the move most with mobile phase, has least interaction with the stationary phase, and particles which move least with the mobile phase has strong interaction with the stationary phase. In the TLC, the mobile phase always acts as the carrier, and whole retention mechanism depends on the interaction of solute with the stationary phase. This slide shows one type of classification of chromatography on the basis of retention mechanism. There are two types of retention mechanism can be involved in the adsorption retention of the solutes: adsorption and partition. In adsorption, stationary phase is solid and the mobile phase can be liquid. If liquid or gas, when it is liquid, it can be column chromatography or thin layer chromatography. In case of partition chromatography, stationary phase is liquid and mobile phase can be gas or liquid. If it is liquid, it can be column chromatography, paper chromatography or thin layer chromatography. Among all the chromatographic methods, thin layer chromatography is the simplest and least expensive method which can be used for the separation of the non-volatile compound. By this method, we, uh, we can analyze the compounds by quantitatively and qualitatively, and also this method can be used for the purification of the compounds. Similar to other chromatographic methods, thin layer chromatography also consists of two phases: a mobile phase that is generally developed in solvent, and the stationary phase, a coated plate or strip. In thin layer chromatography, the shape of the stationary phase is plane. That's why it is known as planar chromatography. It is one of the examples of one-dimensional chromatography. There are three main objectives of thin layer chromatography: identification, separation, and purification. That means with the help of TLC, we can identify, purify to the some extent, and TLC has the power to separate the compounds. On the basis of aim of the thin layer chromatography. We can divide the thin layer chromatography in two types. Analytical thin layer chromatography that is only used to determine the chemical composition of the sample. Second one is the preparative chromatography, preparative thin layer chromatography that is used to purify the compounds and after purification, collection of one or more components of the sample. On the basis of retention mechanism, thin layer chromatography can be adsorption thin layer chromatography when stationary phase is solid, partition thin layer chromatography when stationary phase is a liquid adsorbed on solid. Here we are discussing thin layer chromatography with solid stationary phase. So it is also known as adsorption chromatography. In adsorption chromatography, stationary phase is known as adsorbent. Adsorbent is a substance which is porous in nature with high surface area that can adsorb substances onto its surface by intermolecular forces. Adsorbent should be inert, should be stable for long period, should be colorless, especially when we are working with the colored compounds. It should be easily available and economic. And main thing, it should be of suitable particle size that can provide good separation and reasonable flow rate. Now we come to the part of stationary phases for adsorption chromatography, adsorption thin layer chromatography. These are the stationary phases which are generally used in the PLC. Silica gel with binder gypsum or starch, alumina, cellulose powder, charcoal and activated carbon. Silica gel G. G stands for gypsum, which is used as binder. All these materials differ in their particle size and hence very they play a very important role in separation science. If we talk about the nature, their polarity, their nature ranging from polar to non-polar. Cellulose is considered as the polar stationary phase, whereas activated carbon or activated charcoal is considered as the non-polar stationary phase. Whatever the stationary phase, they are all supported to apply or supposed to apply on a thin layer glass plate or aluminum sheet. That means whatever the stationary phase which are using for the TLC, but these stationary phases are coated on a support material that can be a thin glass plate or aluminum sheet. On the basis of the polarity of stationary phase and the mobile phase, the most common type of TLC. There are two main classes of TLC. Normal phase thin layer chromatography. In normal phase thin layer chromatography, when the stationary phase is polar, like silica gel, and the mobile phase is an organic solvent or mixture of organic solvent, which is less polar than the stationary phase. Reverse phase TLC, when the stationary phase is silica, but the polar silica groupings are bonded with an organic substrate that is non-polar like C18 molecule, octadecyl molecule. And the mobile phase is a mixture of water and organic solvent, which is more polar than the stationary. Here you can see in both type of chromatography, we are talking about the comparative polarity. In normal phase chromatography, organic solvents or mixture of organic solvents should be less polar than the stationary phase. Whereas in the reverse phase chromatography, the polarity of the mobile phase should be higher than the stationary phase. This slide shows the preparation of the silica gel. Silica gel is prepared by the sodium silicate with in acidic medium. And first there is the formation of orthosilicic acid. Orthosilicic acid after condensation converted into colloidal polymer, and this colloidal polymer after condensation and cross-linking is converted into silica gel. Now we discuss the principle of thin layer chromatography. In thin layer chromatography, liquid mobile phase is adsorbed on the solid stationary phase. In every type of stationary phase, the necessary condition is to attain equilibrium between the stationary and mobile phase. So, the equilibrium between the liquid stationary phase and the mobile phase responsible for the separation of the different solute. Here you can see these are the mobile phase molecules which are adsorbed on the stationary phase. The mechanism of adsorption is based on the process of adsorption-desorption. Here you can see at the active part of stationary phase, the solute molecules are attached or retained. As the solute moves with the mobile phase in the stationary phase, there are several adsorption-desorption processes. Then that means separation is due to a series of adsorption-desorption process. And during this, there is the competition of active adsorption sites between the material to be separated and the developing solvents. Here you can see the interaction of analyte with the mobile phase and the stationary phase. How the analyte distributes between the stationary phase groups, stationary phase chemical groups and the analyte molecules. In case of silica gel, at the silica gel, the surface has filled with hydroxyl group, which make it highly polar. And polar functional group can bind in the two ways. Hydroxy groups are polar, so they can bonded with the polar substances through the hydrogen bonding or through the dipole-dipole interaction. Here you can see that this compound is bonded or attached by dipolar interaction, and this is the ketone molecule which is attached by hydrogen bond. As the polarity of the molecule increases, the interaction or bonding becomes stronger and the compound will move slower with the mobile phase. So, on the basis of the principle like dissolves like, polar stationary phase bond make a strong bond with the polar molecules. So, their movement with the mobile phase will be lower or slower. This slide shows the dipole interaction of analyte during the chromatography. If in the sample or mixture, it is a mixture of polar and non-polar molecules. Polar molecules are held by the dipole-dipole interaction of hydroxy groups of silica, whereas non-polar molecules are passed rapidly through the column with the or through the thin layer plate with the flow of mobile phase. Now we come to the procedure of thin layer chromatography. The first step is the preparation and activation of TLC plates. For the as support material, generally glass plates and aluminum sheets are used. Glass plates with different dimensions are available. 20 by 20 centimeter, 20 by 10 centimeter. These slides are generally used for preparative chromatography. 20 by 5 centimeter, and in the laboratory level, microscopic slides 5 centimeter to 2 centimeters are generally used. These glass plates should be of good quality that can bear high temperature, and when we coat the TLC plate for the coating of the stationary phase, if we are taking silica gel, first is to prepare a slurry by mixing 1 part of silica with 2 parts of water. For example, if we are taking 10 gram of silica gel, then it mixed with a 20 ml of water and prepare a homogeneous slurry. After the formation of slurry, this slurry is coated on the TLC plates. Methods used to prepare TLC plates. Generally, 4 methods are used to apply adsorbent on the glass support plate or TLC plate: spreading, spraying, pouring, and dipping plate in slurry. This slide shows coating of TLC plate by pouring. In this method, pour the slurry on glass plate. Slurry is prepared by mixing 1 part of silica gel with 2 parts of water. So, pour the slurry on glass plate with the help of the pipette or any other flask and move the plate around. Spread the slurry uniformly on the glass plate like this to form a thin layer of adsorbent about zero point 0.2 to 0.3 millimeter. So first step is pour the slurry on the glass plate and with the help move the plate around to spread the slurry evenly on the glass plate and to form a thin layer of the stationary phase. During this process, make sure that there should not be uneven spot on the plate. Main drawback of this method, it is a time consuming method because at a time you can coat only one slide or one TLC plate. The second method is the coating of TLC plate by spreading. In this method, at a time 10 to 12 TLC plates can be coated. In the first step, you can see we are taking small TLC plates. These are generally known as microscopic slides. All the slides are arranged evenly on the plane surface or flat surface, and by arranging them, prepare a TLC bed, and this TLC bed is tied up at the top and bottom with the help of a thin paper and the cello tape. So this is the TLC bed. After the preparation of TLC bed, pour the slurry. Slurry which is prepared by mixing 1 part of silica with 2 parts of water. Pour the slurry from one end of TLC bed to another end. After the pouring, with the help of a thin, with the help of a glass rod, spread the slurry evenly by applying very small pressure. In this way, a uniform layer of adsorbent is formed. Similarly, you can follow the same procedure to coat the big size glass plate with the slurry. These TLC plates can be used for analytical studies to identify the components of mixture and also to check the purity of the sample. It is very important to note that always use forceps to handle the TLC plate or do not touch the silica layer of the TLC plate. Otherwise, it can cause damage of the stationary phase and also can cause contamination. Next step. Next step is the activation. After coating, dry these plates at room temperature, and after drying at room temperature, place them in hot air oven at 105 degrees centigrade for 3 hours to activate them. After 2 hours or 3 hours, remove the plates from the oven, and now TLC plates are ready for analytical purposes or analytical studies. It is important to note that um, Always, you can also store these plates to protect from the moisture, and you can use these plates within 3 days. Next slide shows the performing the TLC experiment. First is the sample application, which is known as spotting. In this, on the TLC plate, first draw guidelines with the very light with the help of the pencil. Dissolve the solid substance or mixture which is going to be separated. Dissolve solid sample in a suitable solvent, and with the help of the TLC capillary tube, transfer or spot the dissolved sample on the guideline. Development of the TLC plate. In To develop the TLC plate, take a clean and dry chromatographic jar or beaker. To make sure that the environment in the beaker is saturated with the solvent vapors. For this, rinse the walls of beaker with the mobile phase. Add the mobile phase to the jar and close it to maintain the equilibrium. And when we place the after this, place the TLC spotted TLC plate slightly diagonally in the beaker. Initially, the label of the mobile phase should not touch the spots. The spots, as you place the TLC plate in the mobile phase, spots are moving with the solvent mobile phase. These solvents can move with different velocities or with the same velocities. After the separation of the compound, next part of the study is the calculation of the RF value, or with how we can report the results of the thin layer chromatography. These results are reported in terms of retardation factor. Retardation factor or RF value is the distance traveled by the analyte divided by distance traveled by the mobile phase. Mobile phase always travels the maximum in case of thin layer chromatography. Samples can not travel more than the mobile phase. Sometimes sample can travel equal to the mobile phase but not more than the mobile phase. RF value can never be greater than 1. If it cannot be greater than 1. If it is greater than 1, that means the distance traveled by the analyte is greater than the distance traveled by the mobile phase. The ideal RF value is in between 0.25 to 0.75. If the RF value is 0, it means the sample, the distance traveled by the analyte is 0. That means sample do not travel. It shows a strong interaction of the compound with the stationary phase. And sample is very similar in behavior with the stationary phase. If the RF value is 1, that shows analyte has high interaction with the mobile phase and no interaction with the stationary phase. If the distance traveled by the analyte is similar to the distance traveled by the mobile phase. So RF value is more, that means less interaction with the mobile phase. RF value is less, that means more interaction with the stationary phase. These are different factors which affect the separation method in thin layer chromatography. Temperature, solvent, concentration of the sample, thickness of the layer, and impurities. Temperature is always, during the experiments, temperature should be moderate. If the temperature will be high, then the mobile phase can be evaporated. Solvent. Solvent always selected on the basis of the polarity of the compound. Concentration. Sample must be dilute or put in the form of small spot. TLC plates. Always use TLC plates with minimum thickness of the stationary phase. If the sample has impurities, then unnecessary it will produce a different spots on the TLC plates. How can we know the distance traveled by the sample? If the sample is colored, then the visualization is very easy. If the sample is not colored, then there are different methods of visualization. We can divide these methods as destructive methods and non-destructive. What is the meaning of non-destructive? TLC plates, UV visible light source is used as non-destructive method. TLC plates, one visualize, it can visualize after and after under the UV light source. There is no change in the um, sample of the compound. Sample behavior or sample functional goals. Second one is the destructive method. In destructive method, we can generally spraying reagents are used or spraying of dilute sulfuric acid. When we spray with the dilute sulfuric acid, the spots or the compounds corresponding to the spots are oxidized and different spraying reagents are available. Iodine. Iodine for iodine containing for nitrogen compound containing compounds, iodine is used as the spraying reagent and spots are appeared as brown on yellow background. 2% nilhydrin solution is used for the separation of or for the detection of amino acids. Drag and drop reagent is used for the alkaloids and iron 2-thiocyanate reagent is used for peroxy compounds. After the visualization, next part is recovery and analysis of the sample. First step, scrap the bands separately from the TLC plates. After the scrapping, elute each band with a suitable solvent. By eluting in suitable solvent, may subject it to spectroscopic analysis and or we can evaporate the eluting solvent to obtain the pure compound. Now we come to the last part, application of TLC. First application, preliminary determination of purity of a compound. To do this, always compare the pure compound with a sample compound having impurity. For this, we take TLC plate and put two spots, A for known or pure samples and U for sample with unknown impurity. After TLC, if we get two spots for U samples, that means for unknown samples, that means it contains some purity of one compound. If it has only one spot or of the same RR value, it means the unknown compound is probably the pure compound. For example, in the organic synthesis, if we want to prepare p-nitroaniline, the starting compound would be acetanilide. Acetanilide, after nitration and hydrolysis, it is converted into nitroaniline. First step is the nitration. For the nitration conditions are very lower temperature and by using concentrated acids, mixture of concentrated nitric acid and concentrated sulfuric acid. These conditions prevent or minimize the formation of orthonitroacetyl, but it is formed as the minor product. After the nitration, para-nitroacetyl is formed as the major product, orthonitroacetyl is formed as the minor product. It is formed in the small quantity, and after hydrolysis they are converted into para-nitroaniline, and which is contaminated with the orthonitroaniline. Sometimes it may be possible we got the 100% pure compound. If we want to check the purity of the compound, we can use TLC. For TLC, if here you can see the three spots 1, 2 and 3. 1 stands for orthonitroaniline, P stands for para-nitroaniline. These are the standard compounds which are already available in the laboratory. And third is the mixture which is obtained after the reaction. In the first step, we place or spot these three samples, and for their separation, use mobile phase mixture of 90% hexane and 10% ethyl acetate. Out of the two compounds, orthonitroaniline and para-nitroaniline, if we discuss the polarity of the compound, orthonitroaniline, in orthonitroaniline, both the polar groups are involved in the intramolecular hydrogen bonding. Due to intramolecular hydrogen bonding, the polar groups are not remains free to bond it with the stationary phase. Their polar groups are involved in the hydrogen bonding, so the polarity of the compound will be less and they move fastest with the non-polar hexane of mobile phase. This is orthonitroaniline, and para-nitroanilines are intermolecular hydrogen bonded with the molecules of nitroaniline and with the molecules of stationary phase. So they are strongly retained. In this way, by TLC we can separate the reaction mixture of ortho and para-nitroaniline, or to check the impurity of orthonitroaniline in para-nitroaniline. Second mechanism, second application, following reaction progress. If we want to check the completion of the reaction, three steps are there. Spot starting material. Here you can see spot starting material separately that is available, and reaction mixture. At 0 minutes, there are two spots, that means in the two similar spots that shows in the reaction mixture only starting material is present at the beginning. After 10 minutes we get two spots in case of reaction mixture. One corresponding to the starting material. This shows reaction mixture has still some amount of starting material, that means reaction is not complete. After 20 minutes, the spots corresponds to starting material will disappear, that means there is no starting material, only the product is the other spot is formed that corresponds to the product. So on the basis of this type of studies, we can conclude how much amount of time is required for a particular reaction. Third application, with the help of TLC, we can find out the presence of adulterants in the food sample. In case of red chili powder, azodyes are generally present as adulterants. These azodyes are carcinogenic in nature, and generally Sudan 1, Sudan 2, Sudan red, and Sudan orange G and para red dyes are used for the purpose of adulteration. If we want to check adulteration in red chili powder, we can use thin layer chromatography. For this type of analysis, it is necessary to we have the uh, standard compounds. Here you can see A, B, C and D. In the previous slide, A corresponds to Sudan 1, B corresponds to Sudan 2, C corresponds to Sudan red and D corresponds to Sudan orange G. On TLC plate, P. P stands for pure chili extract. That means dry red chilies are crushed, grind and prepare their extract in a suitable soil. S is sample extract. That means sample chili powder purchased from the local market. A is the spot of Sudan 1, B Sudan 2, C Sudan orange or D Sudan red. For the TLC, again we are using mobile case of mixture of 90% hexane and 10% ethyl acetate. After the TLC, different spots are. Here you can see these two spots are similar. These are the two spots where this spot corresponds to the dye present in the sample chili powder and this spot corresponds to D. D means um, Sudan orange dye. Now that these spots are similar with RF value, same in color and same shape of spots. How we can analyze these spots? Scrap both the spots separately from the TLC plate. Dilute each spot with a suitable solvent like methanol if we want to oh, analyze by spectrophotometry. If we subjected these samples to UV visible spectrophotometry, these are the two spectrums obtained by sample red chili powder and that is denoted by red and violet dye from sample chili powder. Red indicates the dye present in the standard compound and violet represents the dye present in the sample. Here you can see the shape of the spectrum and the value of lambda max is exactly same. So we can say the sample red chili powder is adulterated with the Sudan orange G dye. In this way, we can use thin layer chromatography for the purification uh, of the sample to check the reaction conditions and to check the adulteration